Dear students, in this module we're going to start work on a step-by-step case study in order to better understand mass spectrometry-based proteomics. As you know, proteomics is the study of protein sequence and structure, and the mass spectrometry-based proteomics helps you to identify and characterize proteins. So for that, you first have to perform the measurements on the intact protein, and then you have to fragment these proteins to look at the fragment masses. As an example, we'll start with step 1, that is the measurement of the monoisotopic mass. So the monoisotopic mass of a protein is the mass of the protein obtained after adding up all the elements, all the atoms inside the protein, and you come up with a number. However, there are several types of masses. For instance, the average mass, the nominal mass, and the monoisotopic mass. So when I refer to monoisotopic mass, what exactly do I mean? So I'll talk about it in a moment. So once you have obtained the monoisotopic mass, then this is the MS1, and you can use it towards the measurement of the peptide and protein. Dear students, the naturally occurring elements in nature, for instance, hydrogen, carbon, nitrogen, oxygen, phosphorus, and sulfur, all have various isotopes. In case of hydrogen, you have hydrogen 1 and hydrogen 2. So, if you have two different isotopes, it means hydrogen may exist with two different mass or molecular weights. Moreover, the abundance of each isotope varies. For instance, hydrogen 1 has an abundance of 99.9%. So if you were to select hydrogens from 100 hydrogen atoms, there are 99.9% chances that you will have a hydrogen 1. However, there is this very small chance, that is 0.01%, that the hydrogen element that you will select will be hydrogen 2. So these variable masses and variable abundances lead us to a variable molecular weight for the entire protein molecule. All the proteins, as you know, comprise of these elements that are listed in front of you. So in order to calculate the monoisotopic mass, you have to look at the most abundant isotope. For instance, in this case, hydrogen 1 is the monoisotopic mass. For carbon, carbon 12 or 12.00 Daltons is the monoisotopic mass. For nitrogen, 14.0031 is the monoisotopic mass, and so on and so forth. So the two things that you took from the previous table were, one, that all elements that comprise a protein have multiple isotopes, and second, each of these isotopes occurs with varying abundance. Before I move on, I would like you to be introduced to the other types of mass definitions. For instance, the nominal mass. The nominal mass is simply the integer value of the monoisotopic mass. For carbon, it is 12. For hydrogen, it is 1, and so on and so forth. The average mass is molecular weight of an isotope multiplied by the abundance plus the molecular weight of the second isotope multiplied by its abundance divided by 2. So if there are three different isotopes for an element, you will multiply each molecular weight by the abundance of that specific isotope and sum them all up and divide them by 3. So this is called the average mass. However, in mass spectrometry-based proteomics, we will be using the monoisotopic mass. So just to remind you, monoisotopic mass is the mass of the most abundant isotope, which in case of carbon is 12 and in case of hydrogen is 1. Here, I will show you a small software. It's called the Isotopic Distribution Calculator. This software if you provide it with the formula of your protein or the amino acid sequence as shown here, then it can automatically calculate how many carbons, how many oxygens, and so on and so forth, the elements they are there in the protein. And then it draws this graph. So these are the molecular weight of all the isotopic combinations that can be generated for this protein. Now, if I were to ask you to give me the monoisotopic mass, you would simply go and pick up the highest peak, and that will be the monoisotopic mass. It is necessary to talk about the monoisotopic mass because you cannot possibly compute or even utilize the other masses which do not include the monoisotopic mass. So we always work with the monoisotopic peak. As you can see, there are two experimental data sets here, and there are two monoisotopic peaks that can be observed as the highest peaks. And the peaks other than the monoisotopic peaks that are situated on the right and left of the monoisotopic peak can simply be ignored in further analysis. So in this way, you can simplify the problem of processing the monoisotopic peak. The MS1 gives you an entire envelope of peaks, but using computational tools, you just select the monoisotopic peak from the peak distribution. And that is the mass of the intact protein or the peptide, and you can use it for further analysis.